just to get a warm up on things, let's try a type of question that we could have looked at last time. So let's evaluate the integral from 0 to 3 of the integral from root x over 3 to 1 of e to the, and I don't want this to be ambiguous, so I'll put this in parentheses, e to the y cubed dy dx. And now this won't work out so nicely as written, so let's do this by, and the hint will be part of this question, by reversing the order of integration. Reversing the order of integration. Okay, so let's figure out what's going on here by just perhaps noting that the region that we're integrating over, which we often call D, this is a set of all points of the form x comma y, which satisfy the following properties, right? So we take a look and see that x has to be between 0 and 3. We also see that y is stuck between, at the smallest, root x over 3 and at the largest 1. So the real question for us is, I think we can handle x being between 0 and 3. We can even handle y being less than or equal to 1. The part that's a little confusing is, what the heck is going on? What is root x over 3 less than or equal to y? What's that about? Well, to figure that out, I'd like to just first of all figure out what is the equality version of this. What's the equation? What's root x over 3 is equal to y? What's that? If we can figure that out, then I think we'll be okay. So how about square both sides? X over 3 is equal to y squared. X is equal to 3y squared. We should comment that this is for y greater than or equal to 0 only. Y greater than or equal to 0, well, if you look back here, when you root x over 3, when you take a square root, you're only getting the positive value. Okay, so we could draw a picture then of what we have here so far. Of this region D. If we were to draw a picture of this, I'd think it look something like the following, to be really honest. So we've got an x-axis and a y-axis, and x equals 3y cubed. 3y squared. That's a sideways parabola. Yeah, so it's just stretched out by a factor of 3, but we'll just draw like this. And then see, we're going all the way up to x going from 0 to 3, as we see. If you actually go ahead and compute the point that you get right here, so when x is equal to 3, you end up with y equals plus or minus 1. Of course, where we are right now, we're talking about this right here. Yeah. So then we go back to even what's up here to talk about the region we're talking about. Y is supposed to be stuck between 1 and this curve, right? So we're actually talking about this region in here. Okay. Okay, so let's describe this same region D another way. So this is one way to describe D up at the top, but of course we can also, now based on the picture and the work that we've done, we can say that D is actually the set of all points x comma y, which satisfy the property that, let's just like here we have the constants first, let's go ahead and do that. Y is stuck, as we see in the picture, at the smallest y is 0 and at the largest y is 1. So y is stuck between 0 and 1, and x is stuck between, well, at the smallest x is always 0, and at the largest x is given by, well, this right here, 3y squared. Okay, so that means the original integral, let me just copy paste this down here. So our original integral is the same as if we swap the order of integration, e to the y cubed. Now instead of a dy dx, we're going to end with a dx dy. Now x on the inside is going to go from 0 to 3y squared, and y on the outside is going to go from 0 to 1. Let me mention, oh, why is there so much space between these? Let me mention why this is such a good idea, because if you look at this right here, y is the variable, and how do you integrate e to the y cubed? I'll say we can't. So just maybe the note to make right over here is staring at this part. Integral e to the y cubed dy. Can't do this. We just don't have a way to do this by hand. Now, you might say, well, what's the big deal then? Here we still have an e to the y cubed. Let me get that y cubed in parentheses. Sure we do, but the integral is now with respect to x. So e to the y cubed, that's just a constant right now as far as we're concerned, right? So this, if x is the variable and y is a constant, let me just copy the integral 0 to 1 dy. If we're integrating with respect to x, think about how you integrate 5. The integral is 5x. So same deal here. We'll have e to the y cubed times x. And we're just evaluating x now at 0 and at 3y squared. And if we do that, we'll have the integral from 0 to 1 of plugging in 3y squared for x. So 3y squared e to the y cubed minus, well, now 0 times whatever. So let's just not even write the minus 0 part. So dy. Why is this helpful? Well, now we can do a substitution. Yeah, so now we can say u is equal to y cubed. Earlier we couldn't make use of this substitution all that well. U is y cubed. Du is going to be 3y squared dy. Aha. Also, when, let's see, y equals 0, let's see, u is 0 cubed, we get 0, we got lucky. When y equals 1, u is 1 cubed, which is equal to 1. Oh, we get really lucky updating the bounds here. So I'm not copying the 0, 1 from up here. I'm actually copying the 0, 1 from right over here. And then, let's see, 3y squared dy all becomes a du instead. And then we have the integral, let's see, and then of e to the, well, y cubed, so e to the u. So, whoa, okay. So this will be e to the u evaluated at u equals 1 and u equals 0. So this will be e to the 1 minus e to the 0. Okay, which ends up being e minus 1. Awesome. So here's the funky thing. As originally written, we couldn't even evaluate the inner integral.